This is my intermediate algebra course. Today we're going to continue to learn transformations and the library of relations. If you haven't done the homework completely and correctly from the last class, do that homework before watching this video. In the previous classes, we learned the library of relations, and we reviewed transformations at the left, and we introduced the idea of a relation at the right. You can review that information here if you'd like. As we move along in this class, you're going to need the library of relations right in front of you, along with the transformation properties. But you're especially going to need the library of relations. So please take a picture with your phone, or you can look online. It's going to be called the library of functions, most likely. You're going to need these right in front of you as we move along in this class. So please do not continue unless you get a picture of that so you can have it in front of you. Here's the other transformation properties at the left. So get a picture of that. Now, in the previous classes, we demonstrated transformations by starting with the parent relations. And in each problem, we demonstrated one transformation. We did translation in one problem, and then we did reflection in another problem, and then we demonstrated dilation in another problem, so on and so forth. But today, we're going to do problems that are going to demonstrate all three of those transformations that we've studied. So in this problem, we're going to need translation, reflection, and dilation. So we're graphing more complicated equations. Now, as I mentioned, rotation is really not covered much traditionally in the math curriculum because the math gets a little tedious. So you don't have to worry about that. Now, what we're going to do is we're going to start with the parent graph and the parent equation, and then we're going to transform and modify the equation. Then we're going to transform again and again, and each step is going to demonstrate one transformation for a total of 3 until we get to the final graph, which is the graph of the equation that we're trying to plot. So that's the transformation method for graphing more complicated equations like this one up above. Now, the big problem that students have is they transform in the wrong order. They might dilate first, then translate, then reflect. Or they might reflect first, then translate. Or they might translate first when they were supposed to dilate first, so on and so forth. It's very important that when you use transformations to graph a complicated equation, that you use the transformation properties properly. And you have to be very careful. It's easy to think that you're using them correctly when you're not. But in this class, you don't have to worry about that because I'm actually telling you what order to transform, the order of the transformations. In the next class, we're going to talk about how you're going to figure out what the proper order is. So that said, let's get started. We're going to graph this complicated equation, and you see we have a square root symbol. So we're going to start with the square root parent relation, and you have your library of relations right in front of you. You know that 0, 0, 1, 1, and 4, 2 are reference points that we can use, and we just connect the dots, and there you go. If you forgot what the graph looked like, but you know the equation, well, then you can just plug in 0, then plug in, if you plug in 0, you get that point. If you plug in 1, you get that point. And if you plug in 4, you get that point. Okay, so now we're going to take this equation and rewrite it over here. The yellow equation is exactly the same as the blue equation, no difference whatsoever, except we're adding 4 to x and we're adding 3 to y. Now, why are we doing that? Well, because up here, 4 is added to negative 2x, and 3 is added to y. So we know that we have to get those numbers and those operations there eventually. Now, we learned in previous classes that when you replace y with y plus 3 and x with x plus 4 in an equation, you take the graph of the previous equation and move 4 units to the left and 3 units down. Now, if you're new to my classes, you might say, whoa, wait a second. We're adding 4 to x. So you should move 4 units to the right. And we're adding 3 to y, so you should move 3 units up. Not 4 units to the left and 3 units down. Well, remember, when using transformations to graph, it's the exact opposite of what you would think. So now we know that translation is a rigid transformation. It's rigid. So that means that this shape does not change. The position changes, but not the shape. So we know that if we go up 1 and over 1 from that reference point, the origin, we get the next point. So I'm going to do that down here. So this point went there, and that point went there. And this point is going to go here. So it's the same basic framework. Now, we have a problem. The problem is we're supposed to fill up our window. All right, we have this window here, and we need the whole graph filled. But we have a gap in this area here, so we need another point. Now, there's a number of different ways you can do this. One way is just plug in some x values and hope that you find a perfect square, because we don't want to have to use the calculator. And use this equation. But the problem is this equation up here is pretty complicated. So what I'm going to do is draw temporary axes down here and pretend that that's the origin, and then use the parent equation. If I plug in 9 for x, I get 3 for y. So we're going to count out 1, 2, 3, 4, 5, 6, 7, 8, 9, and then up 3. And we get that next point. Again, there's a lot of different ways you can do that. But you're in intermediate algebra now, so you should be able to do those calculations yourself. And if you want to, you can use a calculator, but I try to avoid a calculator, so that's why we want to plug in a perfect square, 9 or 4 or 1. We could plug in 16, that's a perfect square, but that's out of the window. Okay, so that was the first transformation, and you can see that this equation is much more similar to the equation we're trying to graph. Now, we're going to take this equation that we left off on, and we're going to rewrite it. We're going to write the exact same equation. But instead of x, we're going to write negative x. We're going to replace x with negative x. So when you do that, you reflect the graph of the previous equation across the y-axis. Remember, we learned that in previous classes. Now, again, students are going to say, whoa. You're writing the negative on the x. You're replacing x with negative x, so you should reflect across the x-axis. Again, it's the exact opposite of what you would think. We're reflecting across the y-axis. So what we do is we take a point on the graph of the previous equation, and we figure out what is the distance from that point to the y-axis, and then we go that same distance across the other side. So this point here was reflected to there, and this point will be reflected there, and this point doesn't change positions because it's on the y-axis, and this point is 5 units, 1, 2, 3, 4, 5, 5 units from the y-axis, so we're going to go 1, 2, 3, 4, 5 to the other side, and that gets us there. So now we can connect the dots, and there you go. Now, remember, it's important to understand what we're doing here. We're trying to find the graph of this equation up here. And you can see that this equation is almost exactly the same as this equation here. But there's just one difference. 2 is multiplied by x, or x is multiplied by 2, however you want to say it. You can say either way based on the commutative rule of multiplication. So what we're going to do is we're going to rewrite this equation over here. It's the exact same equation, except we're multiplying x by 2. So what we did was we replaced x with 2x. The transformation properties tell us that when you do that, you take the points on the graph of the previous equation and you divide them all by 2. Now, again, I don't mean to sound like a broken record, but a lot of students would say, no, no, no. We're multiplying x by 2. So that means you have to take all these x values and multiply them by 2. Remember, it's the exact opposite of what you would think. When you transform graphs, everything is the opposite of what you would think. So we're actually going to divide all the x values by 2. So the x value of this point is 4. Divided by 2, we get 2. The x value of this point is 3. Divided by 2, we get 1.5. The x value of this point is 0. Divided by 2, that's still going to be 0. And the x value of this point is 5, or negative 5, that is. Divided by 2, we get negative 2.5. So this point went here, this point went here, this point went here, and this point went there. So we're almost done. Problem is we have an open space here. Now, the easiest way to do this is just to find x values that we can plug in that will create a perfect square inside the root. Again, we don't need a perfect square. We could just use a calculator, but I don't want to use the calculator. So you can just try values, but what you'll find is negative 6 is the only value that's going to give us a perfect square under the root. So plug in negative 6. Plug in negative 6 for x. Negative 6 times negative 2 is 12. 12 plus 4 is 16. Now, why do we care about that? Because 16 is a perfect square. The square root of 16 is 4. Then we have y plus 3 is equal to 4. And obviously you're going to subtract 3 from 4, and we get, subtract 3 from both sides, we get y is equal to 1. So you plug in negative 6, you get 1. So 1, 2, 3, 4, 5, 6, and up 1. Now, a lot of students might say, whoa, whoa, wait a second, you did all that math too quickly. Well, this is intermediate algebra. You're perfectly capable of doing all that math yourself. There's a lot of different ways that you can find a perfect square there. Again, you can use a calculator if you want. You can just choose random x values over here. But I wanted to avoid using a calculator. Now, at this point, I want to remind you the power of this method. This graph is the graph of this equation. And we were able to build that graph step by step using transformations. This equation here is exactly the same as this equation. So the answer to our problem is this graph. All right? So this is a very, very powerful method. But as you're going to find in the next class, there's a lot of potential to make mistakes if we don't use the transformation properties carefully. But again, you don't have to worry about that now. Let's graph this equation for number 2. As you can see, it's a pretty complicated equation, but we know that it's going to be the square root parent relation because we have a 2 power there. So if you look at your library of relations, 0, 0, 1, 1, and negative 1, 1, and 2, 4, and negative 2, 4 are on the graph. So we have our parent graph. Now you see up here, we're dividing by 2, so we need to divide by 2 eventually. So we're going to divide y by 2. So we're rewriting the same exact equation that we have at the left. The only difference is we're replacing y with y over 2. When you do that, you multiply all the y values in the graph of the previous equation. So if you multiply the y values of these points, they go out of the window, so we're not going to worry about those. But if you multiply the y values of these points, you get 1, 2, and negative 1, 2. Again, the x values don't change. And of course, this point here has a y value of 0, so if you multiply by 2, it's not going to change the position. Now, any other points that we could calculate without a computer, they would be off the window, so we can just plot that. Now, what we did is a vertical stretch. We pulled up. We took this graph and pulled up, and we got this purple graph here. So now, you see up here, we have a negative symbol in front of the y minus 4. So we need a negative symbol in front of y eventually. So let's just replace y with negative y. We're writing the same equation over here that we have over here. The only difference is we have negative y instead of y. So now, what that does is it takes the graph of the previous equation and reflects across the x-axis, the exact opposite of what you would think. So again, I know you know how to do this by now, but I just want to be clear. You find the distance from that point to the x-axis and go that same distance on the other side. So that point is reflected to there. And this point is reflected to there. And this point doesn't go anywhere because it's already on the x-axis. Then we just connect the dots and we have our graph. Now remember, this is not an art class. It doesn't matter if your graph is perfect. Okay, so now this equation is exactly the same as this equation. The only difference is, instead of y, we have y minus 4, and instead of x, we have x minus 4. So we have to replace y and x with those expressions. So at the right, you can see that's what we've done. We've replaced y with y minus 4 and x with x minus 4. The transformation properties tell us that when you do that, you take the graph of the previous equation, which is the red graph at the left, and you move it 4 units to the right. So 1, 2, 3, 4, and 4 units up. So 1, 2, 3, 4. So that would get us to there. So this point moved there. And the other points would move, it's a rigid transformation. So that point moves there, this point moves there. And so now we need more points in these regions here. So the easiest way to do this is to draw, I don't want to use this equation because it's going to be pretty complicated. So I'm going to draw temporary axes, and then I'm going to plug in 2 for x because that's going to move us 2 units to the right. And I'm plugging in 2 into the previous equation because we're pretending that this is the temporary origin. If you plug in 2, 2 squared is 4. Multiply both sides by 2, we get negative y is equal to 8. Divide both sides by negative 1, and we get y is equal to negative 8. So what that means is we're going to count 2 units over and go down 1, 2, 3, 4, 5, 6, 7, 8. That's if you plug in negative 2, but if you plug in negative 2, you get the same thing that you get when you plug in positive 2. So positive 2 takes us down to there. There's a lot of different ways to find extra points if you need to find them, but that's just the way that is easiest. If you want, you can just use this equation. You're just going to have to do some more math. Okay, so that is the graph of this complicated equation. And this graph and this graph are exactly the same. So let's do a couple more of these problems. I think you got the basic idea. Let's do a couple more of these problems. We'll go a little faster now. We have a very complicated equation that we have to graph, and you see we have absolute value symbols. So we're going to have to use the absolute value parent relation. And if you look at your library of relations, you know that the absolute value relation, when you graph it, you just get a V shape, and the sides of the V are just straight lines going through the diagonals of the squares on the grid. So now, you see this negative up here, the negative symbol? We're going to replace x with negative x. So our equation and our graph are more, or at least our equation is looks more similar to the actual graph, or the equation we're trying to graph. So because we're replacing x with negative x, we're going to reflect the graph of the previous equation across the y-axis. So we'll take this point and we'll count 1, 2, 3, 4, 5 units from the y-axis, and we'll go 1, 2, 3, 4, 5 units on the other side. But when you do that, notice you just land on a point that was already there. When you reflect this point across, you reflect on top of a point that was already there also. So in this case, when you reflect across the y-axis, you're just going to get the same graph that you had before. Sometimes that happens. So we just draw the same graph. So the negative really doesn't affect much at that point. So now you see we have plus 3 and minus 1. We're going to need those values and those operations eventually. So we're going to replace y with y minus 1, and we're going to replace x with x plus 3. Very, very important to see exactly what we're doing. Our transformation properties tell us that when you do that, you take the graph of the previous equation and you move 3 units to the left and 1 unit up. So I'm going to take this point, move 3 units to the left and 1 unit up. And then we just have the same V shape because this is a rigid transformation. Rigid meaning the shape does not change. So there you go. Okay, now there's just one more thing we have to do. Notice this 3 is multiplied into the y, or y is multiplied by 3. So we're going to rewrite the exact same equation, except we're going to take y and replace it with 3y. When you do that, you divide all the y values of the previous, the graph of the previous equation by 3. You divide by 3, you don't multiply. Again, it's the exact opposite of what you would think. So the y value at this point is 6. Divide by 3, you get 2. The y value of this point is 3. Divide by 3, you get 1. I'm choosing values that are easy. Whoops, that should be there. I'm choosing values that are easier to deal with. Actually, no, that point should be there. If you divide the y value of this point by 3, you get 1. So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And if you divide the y value of this point by 3, you get 1/3. And then we see that, well, we know that the sides of the V are just straight lines. So we can find the slope of the line and use that to help us. So if we go up 1 and over 3, we get the next point. So up 1 and over 3 gets us another point there. And now we can connect the dots. So that is the graph of this equation, which is exactly the same as this equation. So the answer to this problem is here. That is the graph. All right, so let's do one more of these problems. This is a relation that is more difficult. The cubic relation is more difficult to graph. So we see, again, the purpose of this is to graph this complicated equation. We see that there's a third power there, so we're going to use the cubic parent relation. We're going to start by graphing that. 0, 0, 1, 1, -1, -1, 2, 8, and -2, -8 are reference points. But this graph is kind of challenging to have to graph. So if you find that this is difficult to graph, that's okay. It is a little difficult. So we graph the parent relation. Now, you see up here, 2 is added to negative y, and 1 is added to x over 4. So we're going to modify this equation. We're going to replace y with y plus 2, and we're going to replace x with x plus 1. If you do that, you take the graph of the previous equation and move it 1 unit to the left and 2 units down. So I'm going to take the origin point, move it 1 unit to the left, 2 units down, and this is a rigid transformation. So the other points are going to be in the same relative location. So 1, 2, 1, 2, 3, 4, 5, 6, 7, 8. And 1, 2, 1, 2, 3, 4, 5, 6, 7, 8. Yeah, right there. I went a little too far. Okay, so now we connect the dots. And there you go. Okay, so notice that we have a negative symbol in front of the y here. So we're going to replace this y value with negative y. And we're going to graph that equation. So what that does is it reflects across the x-axis. So this point is going to be reflected across. This point is going to be reflected across. And so on and so forth. So when we reflect 1, 2, 3, 4, 5, 6 units from the x-axis, and we go 1, 2, 3, 4, 5, 6 units across the other way. So we get 1, 6. So 1, 1, 2, 3, 4, 5, 6. And this point was on the other graph, so we're going to count how many units to the x-axis and go the same number of units up. And at this point you can kind of see what's going on here. And we're going to be at y equals 10, which is actually there. So now we can connect the dots. And there you go. So again, your graph doesn't have to be perfect, but it has to look like that basic shape. Now, we see that in the equation we're trying to graph, x is divided by 4. So we're going to replace x in the previous equation with x over 4. When you do that, you take all the points of the graph of the previous equation and multiply by 4. So this x value is going to be multiplied by 4, but that x value is 0, so it's not going to go anywhere. This x value is negative 1. Multiplied by 4, you get negative 4. So that's going to be, that point's going to go about there. And the x value of this point here is negative 2. So multiplied by 4, you get negative 8. So that point went there. And this point here has an x value of 1. Multiplied by 4, we get 4. So there. And I think we might be able to find maybe one more point over here. So if we plug in, let's plug in negative 12 for x. So negative 12 divided by 4 is negative 3. Negative 3 plus 1 is negative 2. Negative 2 cubed is negative 8. And so then we have negative y. I'm going to write this down. We have negative y plus 2 is equal to negative 8. Subtract 2 from both sides. Divide by negative 1, and we get y is equal to 10. So if you plug in negative 12, you get 10. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and then up 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Just to be clear what's happening here. So now we connect the dots, and the good news is this equation is this graph is the graph that we're looking for. That's the graph of this equation. This equation that we're trying to graph is the exact same equation that we had in the final step. This equation here. Okay, so now it's time for you to try. So you're going to try number 5, and the first thing you have to do when graphing this complicated looking equation is you have to figure out what parent graph we're going to use and what parent equation we're going to use. Now notice you have absolute value symbols, so obviously you're going to use the absolute value parent graph. So I'm showing you how to do this. So you want to start by looking at your library of relations and graph that parent graph and follow these steps. Now, if you haven't gotten a picture of the transformation properties yet or the library of relations, I'm going to give you one more chance to do that. So after getting a picture of all those, go ahead and try number 5. I'll leave number 3, 4, number 3 and 4 in the window. Try number 5. When you come back, we'll do it together. Okay, we're back. So we already graphed the parent relation for the absolute value equation, so I'm just going to redraw that. And we're going to replace y with negative y because we have a negative symbol in front of the y minus 3. And when we do that, we reflect across the x-axis. So I'm going to take a random point, maybe this point there, and count the distance to the x-axis and go that same distance across. So you know what to do. So that point goes there. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So that needs to go down 1. And the whole graph just flips down. So you know what to do. And now we're going to replace x with 3x because we have a 3 in front of x minus 2. So we know eventually we're going to need a 3. When you do that, you divide all the x values in the graph of the previous equation by 3. Divide by 3, not multiply by 3. So this point here, well, we can use this point down here. That point is it has an x value of 6. So divide by 3, we get 2. So this point here moved there, and the same thing on the other side. And this point here has an x value of 3. Divide by 3, we get 1. Same thing on the other side. And so now we connect the dots. So what we did is we compressed horizontally. It's a horizontal compression. We took this graph and we pushed inwards to get the purple graph. Now, up here we have y minus 3 and x minus 2, right? So we're going to replace y in the previous equation with y minus 3, and we're going to replace x with x minus 2. When we do that, we take the graph of the previous equation and move 2 units to the right. So I'm going to take this point, move it 2 units to the right, and then I'm going to move it 3 units up. Again, it's the exact opposite of what you would think. When you subtract from x, you go to the right, not to the left. When you subtract from y, you go up, not down. And then at that point, we can just use all those reference points. Looks like the slope of those lines is going to be -3. So we use those reference points. Looks like I already had some points drawn. And that is the final graph. That's the answer to this problem. Again, your graph does not have to be perfect, so don't spend countless minutes trying to get a perfect graph. This is not an art class, and even if it were, I don't think you have to be perfect with art. Okay, so that is the answer. We graphed this equation because notice this final equation is exactly the same as the equation up there we're trying to graph. So if you got that answer, excellent. Very good. So now let's move on to number 6. You can try another one of these. Where's number 6? There we go. So try number 6. When you come back, we'll do it together. Okay, we're back. So we have a square, so obviously we're going to start with the square, or the what's called the quadratic parent relation. We already graphed this once today, so you know the reference points: 2, 4, -2, 4, 1, 1, -1, 1, 0, 0. Connect the dots. And but we have an expression divided by 2. -x minus 1 is divided by 2. So we're going to divide by 2. We're going to replace x with x over 2. So what that does is it multiplies all the x values of the points of the graph of the previous equation by 2. So the x value of this point is 2, so multiply by 2 we get 4. Same thing on the other side, there's symmetry here. So this point went there, and this point went there. This point is going to go, well, we're multiplying by 2, so that would be there. And the same thing on the other side. Origin doesn't change places. I think we might be able to come up with one other point, possibly. 1, 2, 3, 4, 5, 6. If we plug in 6, we get 9. So I think that would be off the window. It's good to check, though. Connect the dots, and there you go. All right, now notice that we are subtracting 1 from -x and adding 3 to y in the yellow up there. So we're going to rewrite this equation over here, except we're going to replace y with y plus 3, and we're going to replace x, we're going to replace x with x minus 1. When you do that, you take the graph of the previous equation and you move 1 unit to the right and 3 units down. So I'm going to take this point and move it 1 unit to the right and 3 down. And all the other points, we can use the point that we just graphed as a reference. If we count out 1, 2, 3, 4 and go up 1, 2, 3, 4, we get a point. So I'm going to pretend that this is the origin here and count out 1, 2, 3, 4 and 1, 2, 3, 4. So we get that point there. And same thing on the other side. And we may be able to find another point over here. So let's try plugging in 1, 2, 3, 4, 5, 6. Let's try plugging in 6. But let's pretend that this is the origin over here. And we're going to use the previous graph, or previous equation, that is, because we don't want to use this complicated equation. So let's pretend that this is the origin. We're going to plug in 3, we're going to plug in -6 for x, because we're going to go to the left. 1, 2, 3, 4, 5, 6. That's -6 to the left. And if you plug in negative 6 to x here, we get negative 6 divided by 2 is negative 3. Negative 3 squared is 9. So I'm then going to go up 9. So 1, 2, 3, 4, 5, 6, 7, 8, 9, and that gets me there. So let's just double check that again. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so now we can, I think if we can get the other point, that should be here if we use symmetry. And then we just connect the dots. So we've translated. Now notice in this equation up here, we're well, we have a negative in front of the x. So I'm going to replace x in the previous equation with negative x in this new equation. And remember, if you do that, you just take the graph of the previous equation and reflect across the y-axis. So I'm going to take a point. Let's say we take this point here, and we're going to figure out the distance, 1, 2, 3, 4, 5, to the y-axis. And we're going to go that same distance across the other side. So that gets us to whatever that point was. I think that would be about here. So this point was reflected there. And this point will be reflected on the other side, and so on and so forth. And this point is 1, 2, 3, 4, 5, 6, 7 units from the y-axis, so we're going to go 7 units on the other side. 1, 2, 3, 4, 5, 6, 7. So that's there. And this point is 1, 2, 3, 4, 5 units from the y-axis. So we're going to go 5 units across the other side. 1, 2, 3, 4, 5. So you don't have to take this long to graph every point. We're just taking it slow so you have these concepts reviewed as we go along. So there's the graph. If you got that one right, good job. This is the answer for this problem. That's the final answer there in red. Okay, so let's go on to the next problem. Be aware that you're going to need maybe one more point than we have on our relation in the library. So go ahead and graph number 7. Our window's a little bigger. When you come back, we'll do it together. All right, we're back. We're going to use the square root relation because we have a square root. And if you look at your library, you see 0, 0, 1, 1, and 4, 2 are points that we can use. Those are reference points. But we're going to use 9 also to fill our windows. So 1, 2, 3, 4, 5, 6, 7, 8, 9. And up 1, 2, 3. And connect the dots. And there you go. Now you see we're subtracting 5 from negative 4y, and we're adding 3 to x. So we're going to replace y with y minus 5, and we're going to replace x with x plus 3. When you do that, you take the graph of the previous equation, and you move 3 units to the left. 1, 2, 3, and 5 units up. 1, 2, 3, 4, 5. And we have the same general structure because this is a rigid transformation. So we can go 1, 2, 3, 4, 5, 6, 7, 8, 9, and up 3 to get the next point. Connect the dots, and we're done. Okay, now you see up here we have a negative near the y, so we're going to replace y with negative y. When you do that, you reflect the graph of the previous equation across the x-axis. So we're going to take this point and count 1, 2, 3, 4, 5 units to the x-axis, and then count the same number, 2, 3, 4, 5 across, and that gets us to this point down here. And then we're going to do the same thing with all the other points, and we come up with the following graph. 1, 2, 3, 4, 5, 6, 7, 8, 9, down 3, connect the dots, and we're done reflecting. Now we just have one more thing to do. Notice that we have 4y up here, so we're going to replace y with 4y. When you do that in an equation, you divide all the y values of the points of the graph of the previous equation by 4. Now notice it says don't be afraid of fractions. This problem is going to require a lot of fractions apparently, so we'll see what happens. So the y value of this point here is negative 8. Divide by 4, we get negative 2. So that point went there. And this point here, the y value is negative 7. So don't be afraid of fractions. Divide 7 by 4, or negative 7 by 4, we get negative 1 3/4. So that gets us to here. So that point was transformed to there. The y value of this point is negative 6. So divide by 4, we get negative 1.5. So that point went there. The y value of this point is 5, negative 5 that is. So divide by 4, we get negative 1 1/4. So that point went there. Okay, now we're going to connect the dots, and you see that this curve is kind of flattened out. When you multiply y, that's a vertical compression. So what we did is we pushed inwards, and if there were parts of the graph that were up here, we would have pushed down. We pushed up and pushed down. I guess inwards is not a good way to describe it. Okay, so again, sometimes you have to deal with fractions. Don't be afraid of that. So if you got that answer, excellent. Again, this is the answer. That's the graph of this complicated equation. So now I want you to try number 8. I'll leave 6 and 7 in the window. Now you're probably thinking, well, what about these brackets? Why do you have brackets here? Well, the reason we have brackets is to demonstrate that we're taking this entire expression and raising to the third power. I know that probably doesn't seem very important, but it actually is. And when you use two sets of parentheses, it becomes kind of confusing. So instead of using parentheses on the outside, we're using brackets. But don't be confused by that. You can do number 8. It's the same process that we did before. And as you can see, I walk you through it here. So try number 8, see what you can do. The graph is going to be a little bit more difficult because it's a cubic graph, but try number 8. When you come back, we'll do it together. All right, we're back. So we have a cubic relation here. So obviously we're going to start with the cubic parent relation. 1, 1, 0, 0, negative 1, negative 1, 2, 8, and negative 2, negative 8 are all on the graph. These are points that you should be somewhat familiar with. So that is the parent relation. And you see over here we're dividing by 3, so at some point we're going to need to divide by 3. So now we're going to rewrite the same equation that we have over here except we're going to divide y by 3. And when you divide y by 3, you multiply all the corresponding y values by 3, or the y values of the points in the previous graph by 3. So these points up here, their y values are too big for the window, so we're going to focus on 1, 1. 1, 1 becomes 1, 3. And negative 1 becomes negative 1, negative 3. Again, we're multiplying all the y values by 3. And 0, 0, that doesn't change, and so that's pretty much all we can do. The graph starts to go outside the window at that point. So we dilated. And now you see we have a negative symbol in front of x minus 4. So we're going to need a negative symbol eventually. So I'm going to rewrite that equation up there that we just wrote, except I'm going to write a negative symbol. And usually you would use parentheses, but just to avoid confusion, I'm going to use those brackets just to signify that they correspond to these brackets out here. And so again, you see up here we have this equation. We're rewriting the exact same equation, except we're writing a negative on the x. And what that means is we're going to reflect the graph of the previous equation across the y-axis. So we have a point on this purple graph, 1, 3. It's going to become negative 1, 3. And we had a point down here, negative 1, negative 3. It's going to become positive 1, negative 3. And it's kind of hard to show the graph up there and this graph at the same time. Maybe I can move that up a little bit. But it's difficult to compare these two graphs. But you get the general point. So now we just have to connect the dots. And we've reflected. So now we just have to translate. You see up here, we're subtracting 2 from y, and we're subtracting 4 from x. So we're going to do that. We're going to rewrite the exact same equation that we have over here, but we're just going to subtract 2 from y and 4 from x. So what that means is we're going to take this graph and move it 4 units to the right and 2 units up. So I'm going to take a point, the origin in this case, I'm going to move 1, 2, 3, 4 units to the right and 1, 2 unit up. And then I can just use the general framework. I know if I go to the right one and up one, I get to the next point. Actually, to the left one and up one, and to the right one and down. I said 1, I meant 3. So you get the general picture, connect the dots, and there we are. And again, your graph doesn't have to be completely perfect, it just has to have the right points and the basic shape. My graph is not that great looking, but again, this is not an art class. Okay, so if you got that answer, good job. Now we're going to move on to graphs that require asymptotes. So our first equation is an exponential equation, and obviously we're going to use the exponential parent relation. We have a base 3 exponential expression, so obviously we're going to use base 3. So remember, graphs of exponential relations, they always have a horizontal asymptote on the x-axis. So I'm going to draw that. as a pink dotted line because that'll show up really good. So I've got my pink dotted line there. And it's very important that you use the equation when you graph this, because remember, these equations are different depending on the base. So we have base 3. So we're going to plug in 0 for x, and we get 1. That point is actually always the same no matter what. But then we plug in 1 for x. 3 to the 1 power is 3. And we learned that in previous classes. Remember the exponent rules. I think that's rule number 6, I believe. When you raise something to the first power, you just get whatever the number is. 3 to the 1 power is 3. Then we're going to plug in 2 for x. 3 to the second power is 9. So we go out 2 and up 9. And we have pretty much what we need to graph this, as long as we understand that as we move to the left, our graph gets closer and closer to the x-axis. Now again, my graph is not perfect, but it doesn't have to be perfect. So now we're going to reflect, because there's a negative symbol in front of the y minus 2. So we're going to write a negative symbol there. So we're writing the same exact equation. We're just replacing y with negative y. And when we do that, we reflect across the x-axis. Now that's not going to change the position of the asymptote. So I'm going to rewrite that asymptote. And I'm just going to flip everything across. And there you go. Flipping everything across the x-axis. Again, you want to figure out the distance from a point to the x-axis and go that same distance across the other side. That's reflecting. One way of thinking about it is you're flipping it over the x-axis. Okay, so now you see we're subtracting 2 from y, and we're adding 2 to x over 4. And so we're going to need 2 subtracted and added eventually. So I'm going to rewrite the same equation we wrote above, except I'm going to replace y with y minus 2, and I'm going to replace x with x plus 2. So we're going to take the graph above, and we're going to move it 2 units to the left and 2 units up. So what that's going to do is it's going to move the asymptote up 2 units, but the asymptote is not going to be affected by horizontal movement. But the graph is going to be affected by horizontal movement. So I need to use a reference point. I'm going to use this point here, 0, -1. Whoops, I didn't draw that graph through that point. Sorry about that. There we go. So 0, -1. 0, -1 would be here. But we're going to move it 2 units to the left and then 2 units up. So that gives us kind of an idea of where our new graph is going to be. And then we have this point here, which is 1, -3. So then we're going to start here, 1, -3. And again, we're going to move 2 units to the left and 2 units up. That gives us that point. And another point that we had was 2, -9. So we move that 2 units to the left and 2 units up, and we get this point here. So now we can just connect the dots. So this stuff seems kind of tedious, but as you can see, it's really not that difficult. Okay, so now we're almost done. The only difference between this equation in yellow and this equation in blue that we're trying to graph is that x is divided by 4. So now we're going to rewrite that yellow equation down there, except we're just going to replace x with x plus 4. When we do that, we take the points on the the points on the graph of the previous equation, and we're going to multiply all the x values by 4. Now that's a horizontal stretch. That's not going to affect the horizontal asymptote. If you stretch this asymptote, if you stretch it this way or this way, it's not going to change the way it looks. But it is going to change our graph. We're going to multiply all the x values by 4, so the x value of this point down here is -1, so now it's going to be -4. So this point went there. And this point up here, that's -2, 1, is going to become -8, 1. So this point here became that point, and the x value of this point over here is 0, so that's not going to change positions. Again, we're multiplying all the x values by 4, so now we can just connect the dots and we're done. So I know that seems like a lot of work, but as you can see, it's that if you understand the main ideas, it's really not that big of a deal. Okay, so now let's do another one of those problems that requires asymptotes. So here we have a logarithmic expression, a logarithmic equation actually, and the base of the log is 3, so obviously we're going to start with a parent logarithmic relation with the base 3. And remember, the logarithmic relation has a vertical asymptote. If you look at your library of relations, there's always that vertical asymptote. And logarithm property 9 up here tells us that if you plug in 1, you get 0. So 1, 0 is going to be a point that we're going to mark there. And if we plug in 3, logarithm property 3 tells us if we plug in a number that's the same as this number here, then we get a logarithm value of 1. So we're going to count 1, 2, 3, and then up 1. So we have that point there. And at this juncture, we need to use logarithm property 2. We need to plug in powers of 3. So powers of 3 are 3 to the 0 power, 3 to the first power, 3 to the second power, so on and so forth. So we've already used these principles here. We need to plug in 3 to the second power. If we plug in 3 to the second power, then we get log base 3 of 3 to the second power. And then we can use logarithm property 2 up here. So that's a lot of fancy talk to basically say that that is equal to whatever that exponent is, which is 2. Okay, that's logarithm property 2. I know that stuff seems really complicated, but that's stuff that we've already gone over in previous classes. If you forgot, that's okay, but you need to jog your mind right now. Okay, so now we're just going to plug in 3 to the second power, which is 9. 3 to the second power is 9. So we go 1, 2, 3, 4, 5, 6, 7, 8, 9, and then up 2. Because again, we plugged in 3 to the second power, and the value of the log was 2, the exponent. But 3 to the second power is 9, so we plugged in 9 and we got 2. So we connect the dots, understanding that as we move down, the graph gets closer and closer to that asymptote. Okay, so you can see that up in this equation we're adding 3 to y and subtracting 6 from negative 3x. So eventually we have to do those operations. So in this equation over here, we're going to rewrite the equation here, except we're going to replace y with y plus 3, and we're going to replace x with x minus 6. So the graph is going to be the same graph as the previous graph, except we're going to move 6 units to the right and 3 units down. So if we move 6 units to the right, that's going to move the asymptote, because it's a vertical asymptote. So our new asymptote is there. Now let's focus in on some points here. Let's look at this point here. That point is 3, 1. So 1, 2, 3, 1. And we're going to move 6 units to the right. 1, 2, 3, 4, 5, 6. And 3 units down. 1, 2, 3. So we get there. And we can see that this, so that point went there. And we can see that this other point is 2 units to the left and 1 unit down. So I'm going to connect the dots, and that's it. So we have that graph. So now we're going to reflect, because we have a negative symbol in front of the 3x. So we're going to need a negative symbol around the x eventually. So we're going to replace x in this equation with negative x to get our new equation. And when you do that, you reflect across the y-axis. Now, if you flip this dotted line across the y-axis, it's just going to move it from here to over here. That's going to be about there. So reflecting across the y-axis does change the position of a vertical asymptote, unless the vertical asymptote is on the y-axis. So now we're going to reflect the actual graph itself, and you can see what's going to happen. Those points are just going to flip over to the other side, and I'm going to draw that in red. Sorry, my computer's going kind of slow. Okay, so there you go. This point here, for example, was 1, 2, 3, 4, 5, 6, 7 units from the y-axis. So you just go 1, 2, 3, 4, 5, 6, 7 units to the other side. And the same with the other point. So now we're going to multiply x by 3. Specifically, we're going to replace x with 3x. And obviously that's because we have a 3 multiplied into x, so that means we're going to divide all the x values in the graph of the previous equation by 3. Now, that's going to affect the position of the asymptote, and it's very important that you understand when you do the homework that vertical asymptotes are affected by horizontal dilation. So if you're going to divide all the x values of this graph by 3, you need to first start by dividing the equation of the vertical asymptote by 3. So this vertical asymptote is at x is equal to negative 6. If you were to draw the equation, or write the equation, it's x is equal to negative 6. That's the equation of this vertical asymptote. But because you're dividing all the x values by 3, remember, it's the exact opposite of what you would think. We're not multiplying by 3, we're dividing. You're going to divide that number by 3 also. So now our new asymptote is going to be at x is equal to negative 2. And the reason that we move the asymptote is this is a horizontal compression. Remember, when you have a horizontal compression, you push the graph from the left and from the right. You push it inwards. Now, in this case, there's no part of the graph that's in the first or fourth quadrants, so we're not really pushing anything from the right, but we do have parts of our graph and features of the graph in the first and second quadrants, so we're pushing the graph inwards. And because the asymptote is a feature of our graph, an invisible feature, but it is a feature of our graph, and the points on the graph, they're pushed inwards, it would make sense that the asymptote would be pushed inwards also. So that asymptote it's pushed from here to here. And now you want to take all the x values of the points on that graph, divide by 3. So the x value of this point over here is 7. So divide by 3, we get 2 1/3. So that's going to be, that point is going to be about there. I went too far down though. And this point over here is at -9, -2. So divide the x value by 3 and we get -3, -2. So that point goes to there. And at this juncture, it'd be useful for us to find another point somewhere over here. So the easiest way to do this is to plug in x values so that we get some power of 3. Why do we want a power of 3? Well, because it's base 3 logarithm. All right, it's a base 3 logarithm. So if we plug in, say, -4, we don't get a power of 3. But if we plug in -5, we do get a power of 3. -5 times -3 is 15. 15 minus 6 is 9. And log base 3 of 9, as we just talked about in the previous equations, is 2. Then we subtract 3 from both sides of the equation. We have y plus 3 is equal to 2. Subtract 3, we get -1. So we found one more point. And that is -5, -1. And we can connect the dots, and we're done. So I know that seemed like a lot a lot of calculations we did, and we did them pretty quickly. But again, you have to remember this is intermediate algebra, so you need to be able to do those calculations and understand or have a rough idea of how we calculated. We plugged in -5 for x, we got 9 there, and then we used logarithm property 2 to figure out what that logarithm would be without using a calculator. So we found that the value of that logarithm was 2. And then we subtracted 3, and we got y is equal to -1. So if you plug in -5 for x, you get -1 for y. I know that's a lot to have to do, but again, you need to know your way around logarithms. Okay, so let's do one more of these. We're going to pick up the pace here because we're running out of time. Obviously, we have a variable in the denominator of the fraction, so we're going to use the reciprocal relation. So I'm going to draw the asymptotes. Remember, you always have an asymptote on the x and y axis with the reciprocal relation. Then I'm going to draw those 6 points. You should be familiar with those 6 points. 1, 1, 1/2, 1, 2, 1/2, -1, -1, -2, -1/2, -1/2, and -2. Those 6 points are always the same for the parent reciprocal relation. Again, there are variations of the relation, but the parent relation always has those same 6 points. So now you see we're dividing y by 2. So we're going to rewrite this equation over here, except we're going to replace y with y divided by 2. So we're going to multiply all the y values by 2. Now, because the asymptotes are on the axes, dilation is not going to affect their location. You can consider this horizontal asymptote to have an equation of y is equal to 0. You multiply y by 2, or multiply 0 by 2, it's not going to change that location. So if you consider all the points on the x-axis, or on that horizontal asymptote, they all have a y value of 0. So if you multiply those y values by 2, it's not going to change their location. But all the points on the actual graph, those y values are going to be multiplied by 2. So 1, 1 is going to become 1, 2, and 1/2, 2 is going to become 1/2, 4, and 2, 1/2 is going to become 2, 1. Again, just multiplying all the y values by 2. And the same thing is true on the other side. We have negative 1, negative 1. It's going to become negative 1, negative 2. We have negative 1/2, negative 2. That's going to become negative 1/2, negative 4. And negative 2, 1/2 is going to become negative 2, 1. And we just connect the dots. And there we go. So now we're going to rewrite this equation over here. We're just going to replace y with negative y, because we have a negative symbol out here, and at some point we have to have our negative symbol there. So what that means is we're going to take the graph of the previous equation and reflect across the x-axis. So remember, it's always the exact opposite of what you would think. We're not going to reflect across the y-axis. Even though there's a negative on the y, we're going to reflect across the x-axis. So I'm going to take all those points and just flip them down. So all these points were flipped down over the x-axis, and all the points down here are going to be flipped up across the x-axis. And so those are our points. So again, it's very important to understand the basic idea of reflection. You figure out what the distance is from a point to the x-axis and go that same distance across, and that's how we get the other points. Okay, now we're going to rewrite this equation over here. Same exact equation, no difference whatsoever, except we're going to replace y with y minus 1, and we're going to replace x with x minus 3. Why are we going to do that? Because in the equation we're trying to graph, up at the left, we have x minus 3 and y minus 1. And notice that this equation is now the same as this equation here. So what we can do is take this intersection point of the asymptotes and use that as the center of the action, and we're going to move 1, 2, 3 units to the right and 1 unit up. And so our new asymptotes are there. And if we remember, well, we can just take a point, for example, 2, negative 1, 2, negative 1. Pretending that this is the origin, we can just go out 2 and then down 1. Then we have 1, negative 2, and 1/2, 4. Again, if you pretend that this is the origin, we can find those points pretty easily. And you get the idea. So now we connect the dots. And there's our graph. So this graph here is the answer. That's the graph of what we're trying to do, the graph of the equation that we're trying to plot. So now it's time for you to try. Go in attempt number 12. You can take a picture of these problems if you'd like. These are going to be useful for you in the next 3 problems. We're just going to do 3 more problems. So try number 12, and when you come back, we'll do it together. Okay, we're back. So this is an exponential relation. It looks like I already had one of the points graphed for you, 0, 1. Plug in 1 for x and you get 2. Plug in 2 for x and you get 4. Connect the dots. And there you go. Now, why are we starting with base 2? Well, obviously because our equation had base 2. Now we're going to replace x with negative x. And what that does is it takes all the points of the graph of the previous equation and reflects across the y-axis. That's not going to change the position of the asymptote. So I'm going to just redraw that asymptote. And I'm going to reflect all those points across the y-axis and connect the dots, and there we go. So again, you just take a point, figure out the distance from the y-axis, and go that same distance across the other side. That gives us each point. So you should be familiar with the transformations. Now we're going to translate. We're going to replace y with y plus 6, and we're going to replace x with x minus 2. So that's going to move the graph 2 units to the right and 6 units down. That's not going to affect what the asymptote looks like, so I'm just going to redraw that. Actually, when we move down, it is going to move it 6 units down. So 1, 2, 3, 4, 5, 6. The horizontal movement is not going to affect the location, how the asymptote looks. So there's our asymptote. So let's take a reference point, 0, 1. That's going to be moved 2 units to the right, 1, 2, and 6 units down, 1, 2, 3, 4, 5, 6. So that's that point there. And then we can just use that point as a reference. Go up 2, to the left 1. And we may be able to find another point here, but we'll see. Let's try plugging in -1. You plug in -1 minus 2 is -3, but that's a double negative because there's a negative out here. So -3 becomes +3. 2 to the 3rd power is 8, and then subtract 6 from both sides of the equation, and we get 2. So again, we ended up with y plus 6 is equal to 8. Subtract 6, we get 2. So when we plugged in -1 for x, we got 2 for y. So that gives us another point to graph there. So again, I know that's a lot that we're doing, but you should be able to figure out what we did there. I plugged in -1 for x, and I solved this equation, and I got 2 for y. Okay, so now you see that we have 2 multiplied into y, so we're going to have to replace y in this equation at the left with 2y. And that's going to divide all the y values in the previous graph by 2. Now, it's also going to affect the the horizontal asymptote. So now the horizontal asymptote is y is equal to -6. So if you divide all the y values by 2, it's going to divide all the points on that asymptote, all the y values of the points on that asymptote by 2. So we're going to get y is equal to -3 as our new asymptote. So I'm going to draw that. Sorry, my computer's going kind of slow. Okay, so now we have our asymptote. And now we're going to divide all the points. So this point becomes 0, -1. Dividing all the y values of the points by 2. This point becomes 1, 2. And this point here becomes 2, 2.5. And this point up here becomes -1, 1. And as I notated up here, this point may be a little hard to find, but again, you can just plug in -2 up here and solve the equation. If you do that, you come up with that point. So that is the graph. If you got that right, excellent, good job. So I want you to try number 13. Again, you can take a screenshot of these problems that we did. That'll help you. Number 10 will really help you to do problem 13. Just be aware that you're going to need to move the asymptote in these steps here. So try number 13. I'm going to leave the window open, and when you come back, we'll do it together. Okay, obviously we have a base 2 logarithm, so we're going to start with base 2, log base 2 of x. And remember, we always have a vertical asymptote when you're dealing with log relations. Plug in 1, you always get 0. How do we know that? That's logarithm property 9. Plug in 2, well, 2 is the same as the base. So if those are the same based on logarithm property 3, plug in 2, you get 1. And then we're going to plug in powers of 2. That's this property here. Plug in 4. 4 is 2 to the second power. So we have log base 2 of 2 to the second power. So that value is going to be 2. Plug in 2 squared, and you get 2. So 2 squared is 4. So we plugged in 1, 2, 3, 4, and we get 2. Plug in another power of 2. That would be 2 to the third power. So change that to 2 to the third power. Again, this is all logarithm property 2 that we're using. And then the value of the logarithm would be 3. So 2 to the third power is 8. So we're going to go out 8. 1, 2, 3, 4, 5, 6, 7, 8. And then up 3. And so on and so forth. So connect the dots. And there you go. So now we just have to modify the previous graph. We're going to translate first, so that asymptote is going to move 1 unit to the left. Vertical movement is not going to change the way the asymptote looks because it's a vertical asymptote. And we're going to move all those points 1 unit to the left and 4 units down. So let's take this point here. And we're going to move it 1 unit to the left and 1, 2, 3, 4 units down. And once I get that point, I can look at how all these points are related, how far they are, and then just use that logic to plot the other points. And there you go. So all the points moved 1 unit to the left and 4 units down. Okay, so now we're going to replace y with negative y. And why are we going to do that? Well, because we have a negative y in the equation we're trying to graph. So we're going to rewrite the same equation, except we have negative y. We're going to reflect this graph across the x-axis. Whenever you write a negative on the y, or replace y with negative y, you're going to reflect across the x-axis. So this point here is 0, 0, negative 4. So it's going to become 0, 4. And the position of the asymptote is not going to change when you reflect across the x-axis because it's a vertical asymptote. So 0, 4 is a point we need. And we're just going to reflect all the other points. And we get the following. So let's double check all that. Everything looks right, so let's connect the dots. Understanding that as we go up, we get closer and closer to the asymptote. Okay, so now we're going to dilate. We're going to replace x with x over 3 because we have an x over 3 in our equation that we're trying to graph. So when you do that, you multiply all the x values of the previous graph by 3. So the x value of this point is 0, so that's not going to change. The x value of this point is 1, so that's going to be multiplied by 3. That's going to become 3, 3. And the x value of this point is 1, 2, 3, so multiplied by 3, we're going to get 9. So that's going to go all the way over to here. And the x value of this point, that's 7. You multiply by 3, you got 21. So that'll go way off of our window. Now I didn't mention the asymptote is x is equal to 1. This asymptote here is x is equal to actually negative 1. Sorry. So if we multiply that by 3, we get x is equal to negative 3 for the new asymptote. So I'm going to change the position. So notice that the position of the vertical asymptote changed because it's a horizontal stretch. So we're pulling the entire graph this way or this way. So that means we're going to pull the asymptote also. Okay, so now we can connect the dots, and notice that I said that you don't have to find any points in that region because it gets kind of difficult without a calculator. Okay, so if you got that one right, good job. All right, number 14. Go ahead and try 14. And when you come back, we'll do it together. All right, we're back. So remember, the reciprocal parent relation has asymptotes on the x and y axes. 1, 1, 1 half, 2, 2, 1 half, negative 1, negative 1, negative 2, negative 1 half, and negative 1 half, negative 2. Those are all reference points on the graph. And when we replace x with negative x, we reflect across the y-axis. That's not going to change the position of the asymptotes because they're all on the axes already. And I'm just going to flip those points over the y-axis and connect the dots. And now we're going to replace y with 2y. and that divides all the y values of the graph in the previous equation by 2. But that does not change the position of the asymptotes because, again, they're already on the axes. So divide by 2. And all of our points, this point here is 1, 1, so it's going to become 1, or it's 1, negative 1, so it's going to become 1, negative 1/2. And this point is going to become 1, negative 1/4. And this point is going to become 1/2, 1. This point is negative 1, 1, so it's going to become negative 1, 1/2. This point is negative 1/2, 2, so it's going to become negative 1/2, 1. And this point is negative 2, 1/2, so it's going to become negative 2, 1/4. So we connect the dots, and we get the following graph. Okay, so now we're going to replace y with y minus 1 and x with x plus 2. When we do that, all we have to do is move the graph 2 units to the left and 1 unit up. So I'm going to first move the asymptotes. So this is our intersection point there. So we need to move all the points. So this point here is 1/2, negative 1. If we pretend that this is the origin, we just go out 1/2, negative 1 to get this point here. Then this point is 1, negative 1/2. And this point is 2, negative 1/4. And this point is negative 1/2, 1. Again, we're pretending that the intersection of the asymptotes is the origin. This point is negative 1, 1/2. And this point is negative 2, 1/4. So we'll just connect the dots. And there you go. So if you got that graph, good job. So that was the class today. If you'd like to take screenshots of all the work that we did to help you with your homework or to study for tests, go ahead and do that now. Here's screenshot number 1 and screenshot number 2 and screenshot number 3 and number 4 and number 5 and number 6 and number 7. But don't go before you get your homework. Let's look at the homework. Get a screenshot of the first page, or the first 2 pages of the homework. And another screenshot of the 3rd and 4th page. And a screenshot of the 5th and 6th page. We have the answers at the right. And we have more answers. And one more page. So get that homework done completely and correctly and neatly, and keep it in order in your binder. And when you do this homework assignment, you're going to want graphing paper. You can do it without graphing paper, but it's going to be much, much easier. It's going to be 1,000 times more instructive for you, more educational to use graphing paper. So get that homework done, and I'll look forward to seeing you in the next class.